Welcome everyone. Today we have the pleasure to have Jie Han from Beijing and telling us something about spanning trees in expanders.
Okay, all right. Yeah, thank you for the introduction and also for the invitation for Hong and Jane Kong. And yeah, today is my great pleasure to talk about some of my recent research. And this is enjoying work with Jie Hu from Nankai University. She's currently a postdoc in Nankai University. And then Li Danping, Yi Wang, Guanghui Wang, and Donglei Yang from Shandong University. So the first two are students of Guanghui, and then Donglei is a postdoc in Shandong. Okay, so we'll talk about spanning trees in sparse graphs. It'll be some quick introduction. So some overview. So we consider undirected and simple graphs, and for the binomial random graph will be you have n vertices, and then for every two vertices you connect them by an edge with probability p and independent of others. And so this calligraphic T n delta will be the class of all trees with n vertices and maximum degree delta, or maximum degree at most delta. And then we will not need to go through this concept of universality a lot, but it's just saying when I want to embed a graph, maybe I don't want to restrict on a single graph, I want to embed a class of them simultaneously. And so this is defined with respect to a class F. Then F universal means I embed like all of them there in the host graph. So for trees in dense graph, one should probably start with this really the textbook results. So if your graph has minimum degree k, then you can embed all trees with k edges in your graph. In other words, this G is a T k plus 1 k universal, like n equal to k plus 1. And then somehow, I think Vera Shosh, who passed away 2 weeks ago, or she tried to leave this as exercise in the graph theory class. That's what I heard. But apparently it's hard enough to become an early Shosh conjecture, whereas essentially compared with the minimum degree one, she wanted to replace the minimum degree by the average degree. And then G contains again all trees with k edges. And then for spanning tree, so the classical result is about minimum degree condition, and you say one needs n over 2 plus some mu n to embed, so that you can embed any spanning tree with the maximum degree. Well, the maximum degree is not really constant, it's Cn over log n. And later, people made it exact, so that the not exact, but people reduced the minimum degree condition from linear, from little of n to log n, or some constant times log n. And somehow this is tight, not up to, up to the constant of C, because for some trees, you cannot embed it with just minimum degree n over 2. I believe they are the delta array tree or complete delta array tree. So for those trees, I'm not going to explain in full, but for those trees, you consider a bipartition of it. You put the root there, and then the neighbor's root the other side, and then this side, this side, this side, this side. You don't have much freedom. The bipartition is actually unique, I believe, and it's not balanced. So you can't embed it into K n over 2 n over 2. So that's why you need this extra log on the minimum degree condition. And so what about in random graphs? In random graph, so the first results about just path. What about long path? And then people understand it quite a while now, although the results I show are in 80s. Now you just need to take a P equals C over N, namely the degree constant degree. and then you can embed a very long path, almost spanning. Yeah, and probably I don't go into that, this fraction, but the fraction is vanishing when C is large. And right, and the question of large trees are also, so this the first one is a path. The second one from De La Vega is about trees. So essentially, so yeah, we get almost spanning tree with constant maximum degree. Okay. Then, so the tree universality was first raised by Alon, Krivelevich, and Sudakov, and they show that this GNC over N contains all trees maximum degree, bounded maximum degree, and N minus epsilon N vertices. So when I spoke about universality, it's somehow when you get one, you get another, but that somehow doesn't, it's not a real issue if you have deterministic graphs, because usually when you can embed two of them separately, somehow you have them both of them automatically. But this is not true for random graphs if you want to make your conclusion to be asymptotically almost vertic or with high probability. Because when you make an embedding result, you say, oh, my graph contains this tree with like a fading probability super small. But there are exponentially many such trees. You cannot make your conclusion like free. You still need like to argue it. And a better bound, the better bound on C was obtained by Balog, Chaba, Pei, and Samoti using a tree embedding theorem of Hexel. Okay, so right, then these are really not about spanning trees. What about spanning trees in GMP? And this was, well, this was a conjecture of Khan. He said, or he conjectured that the probability, optimal probability will be log n over n. And then you get a bounded degree spanning tree. And there are partial results by Alon, Krivelevich, Sudakov, and Hafiz, Krivelevich, Szabo. And well, but it is done now, or it was done by Montgomery, who proved it, but not only the single trees, but also the universality result. And the single containment was later also recovered by these breakthroughs of excitation threshold or fractional excitation threshold. Both of them recovered this, but not both recovered a single containment result, but not a universality result. So Montgomery's result still stands as an excellent piece of work right there. And yeah, it's more than 60 pages. Maybe I never really read it seriously, but yeah. So that's kind of a period about spanning trees in random graphs. And then what else can we do? This is a small separate result, small separate project raised by Krivelevich and Sudakov in particular. So what about spanning trees in randomly perturbed graphs? Namely, you want to start with a deterministic graph with usually a mean degree condition, and you drop random edges on top of it. And then, so Krivelevich, Kwan, and Sudakov show that if I start with arbitrarily weak minimum degree gamma n, like dense, and then I put linearly many random edges, and the resulting graph has any bounded degree spanning tree. This minimum degree condition, you want it to be dense, then gamma to be arbitrarily small is definitely smallest, and this linearly many random edges is also kind of needed. So the question is, can you make it like universality results, right? So for single containment, they have failing probability, but again, you cannot just multiply by the number of such trees exponentially many. But can you make it? And somehow in 2019, we made it with Julia Bocher, Yoshi Kohakawa, Richard Montgomery, Olaf, and Yuri person. And yeah, again, as I try to emphasize this universality thing, it's kind of mysterious actually to me until now. I mean, we didn't have a way to deal with these error probabilities. The way we made it is to prove it by replacing the Gn C over n by certain pseudo-random graphs. And then we are in the world of a deterministic graph, so we don't need to worry about the probabilities. Sorry. So, and then this is the how we did it, or how we proved the conjecture. And here I want to introduce a slight strengthening of that result. For that, we introduce this bipartite whole alpha star condition. I'm not defining as in the Mike Dermot's paper, but yeah, I found this condition to be easy. So you just say the largest T for which you have two vertices, two disjoint vertex sets of size T, and there's no edge between them. I don't need them to be disjoint, like bipartite whole or bipartite independence members or so. And then for a quick remark, so this Gn C over n, the alpha star number for it, it's about n over c, or n over c to the power 1/3. And then what essentially we proved in that paper is that if you take a graph G with minimum degree gamma n, and then you take a G prime, which is a pseudo-random graph, and we don't really need it to be super pseudo-random. We only need to have alpha star condition to be alpha n, and delta, and the maximum degree to be 1 over alpha is some constant but related to alpha. Right. And then we show that this union of G and G prime is T and delta universal, contains every bounded degree spanning tree, and then it's universal automatically because there is no probability involved. Right. And then the improvement, or the slight strengthening is when, oh, sorry, we have submitted, so it should be 23 plus or 22 plus. Sorry. Now we don't need to distinguish two graphs, or if you still think of the two graphs, just for the pseudo-random graph, we don't need the maximum degree condition anymore. Or actually, if you realize that, then you can put them together. You'll only need one graph, G, and then minimum degree gamma n, and alpha star G is at most alpha n. And then this is enough to make it T and delta universal. Any question, or does the result make sense? Or okay, and somehow in the paper, or I mean, in the early paper, 2019 paper, we somehow really need this delta condition when we count stars. When we did absorbing, when we do absorbing, we really needed delta number, delta condition, maximum degree condition for counting stars in the when building the or choosing the absorbing sets, and somehow now we don't need it. Well, right. So next result is about in expanders, and in expanders, here is essentially the argument, or the theorem of sorry, not argument, the result of Hexel, and then she showed that very general results, very weak, or in some sense best possible conditions for having a tree, but not a spanning tree. So the conditions are also natural. You get a set when it's smaller than some threshold m, then it expands with the ratio d, and then it's between m and 2m, then it expands a little bit faster. It's not faster, it expands a little bit more. Then you can embed every tree with m plus l vertices. If you do it carefully, you can slightly grow to an almost spanning tree. Like each time you make sure you are in good shape, but this will not give you a spanning tree anyway. Right. And so we will go to this expander definition of Johansson, Krivelevich, and Samoti. But whoops, sorry. Let me mute. Okay, so right. That's about the two natural. I mean, I think Hong did a lot of research on that. And then again, it says small sets expand and large sets, they're connected by edges. And that's it. And it's easier or more natural or weaker than the lambda graphs and this pseudo randomness. But somehow also natural because when we are embedding trees, we don't need like highly connected substructure. Somehow this like for large set where one edge is possibly is somehow enough, right? So, right, by just applying Hexel theorem, and they show that every ND expander is not Tn delta universal because you don't get spanning tree, but you miss a small proportion of vertices. If you think about delta is a constant, then this is 1 minus epsilon times n. Yeah, sorry. And right, so the goal will be find the minimum d or the smallest possible d so that ND expander is Tn delta universal. So that is the goal or like of this talk or so. And then so Johansen, Krivelevich, and Samoti, they were able to do to finish to get a spanning tree with this d. Like d is delta times n to the 2/3. But again, that's not only for constant delta. So their delta can also grow up to n to the 1/3. And then what we did, compare with them, joint work with Donglei Yang from Shandong. So what we did compare with theirs is like we have a smaller d. So they had 2/3, we have one half, like 0.5. And also we allow somehow bigger delta. But probably again, this side is not very important in people's mind. I mean, what they're really interested about, what can you do about just the boundary degree trees. And for that, yeah, we could do more. For boundary degrees, we could do delta to the power of root log n. So, so if its delta is little 1, this is smaller than any polynomial. So this is what we can do. Yeah. But like how good or how is it? For that, we jump to ND-lambda graphs. So quick one sentence definition, or ND-lambda graph is a deregular graph, n vertices, and the second eigenvalue at most lambda in absolute value. And so Alon, Krivelevich, and the Sudakov, they show that a constant spectral gap. When I speak of a spectral gap, is the lambda over d, or d over lambda, sorry. Spectral gap usually is d over lambda. But anyway, this is constant. What is there is constant. A constant spectral gap guarantees almost spanning tree. And then their conjecture or question will be just, does constant spectral gap give you a spanning tree? Or like universality, but universality somehow does here, it's not really important because you get it automatically. But maybe just saying, oh, you do not just give me a Hamiltonian path, you give me all the boundary degree trees. Right, so unfortunately, this is the question. So essentially, what we proved here is some bounds smaller than any polynomial, but they want constant. They want constant. Okay, so right. That is the question. And then even for Hamiltonian path, it's not completely solved. But we've got the recent result of Stephen Clark, David Mola, I don't know, sorry, Corella, and Benny Sudakov, who made a breakthrough for the Hamiltonian path, actually Hamiltonian cycle case, and they proved that if lambda is at the most d over log n to the 1/3, they could solve the conjecture. Well, they could find Hamiltonian cycle, or if D is a polynomial, say D is n to the some little of 1, then they could, and then with constant spectral gap, they could build a Hamiltonian cycle. So what we proved, or our result in the expanded arrow translates here to give a similar band. Spectral gap to be some subpolynomial thing, like a constant or 2 to the root log n will be enough. Okay, so any question again? But I'm just, yeah, I will try to convince you to, I will try to tell you how we get this bound, and then hopefully what to do next, but probably I don't have a good idea, but yeah. So, right. Starting from this, actually, or let me see, all the results we kind of know on this random graph or pseudo-random graphs, they don't really take the trees because the trees are really diverse. They have different trees, so they kind of all of them split the trees into cases, at least 2 cases, and this was done by Michael Krivelevich, and then he observed, or he proved, that every tree, n-vertex tree, either has n over 4k leaves or at least n over 4k vertex disjoint bare path, each of length k. And by bare path, I mean the paths with interior vertices of degree 2, so they don't have any leaf or branches attached to it. And the k is, n is your number of vertices, and the k is a parameter you can choose. And for that, for example, Montgomery's result used this dichotomy and then splits into 2 groups. And then I could, for the first one on the left-hand side is a many leaf case. And actually, he could just apply the result of Alon, Krivelevich and Sudakov, which embeds an almost spanning tree in GMP, with p is like log n over n. And then you have a small leftover. If you are sure your graph has many leaves, your tree has many leaves, you take the leaves out, like epsilon n leaves, you take them out, you embed the almost spanning tree, and now the rest of the job is to match them by a star matching. And for that, you can expose another copy of your GMP by multi-round exposure, a simple trick, and then you just find the matching by Hall's condition. This is like how this case is handled in Montgomery's proof. He didn't even write it down because this done. I mean, right. So for him, for his result, the hard part is about the case where your tree has many bare paths. So this is done by multiple connection, or done by him by multiple connection, and absorbing played an important role in his proof. So that is the right-hand side picture. On the right-hand side, you have some set of ends of this bare path, and you need to connect them simultaneously by vertex disjoint paths, and you need to make sure the exact lengths, because when you fix those parts, by putting down an almost spanning tree, now the 2 images in green, I mean the dots in green, are already fixed. Then you need to connect them by exact lengths. So that is that's where he applied this absorbing method to make sure the lengths are exact. And also the absorbing device provides flexible ways to make this simultaneous connection. Okay. And this is the star matching result we will need, but probably I don't go to detail what you can imagine is when you are at your last step, you have a group of leaves. Now you don't have them. You have like vertices. You want to embed them as the images of leaves, and you have their parents already there, and you want to find the star matching, or you can think about perfect matching, but between them, and for that you need some mean degree condition. You otherwise say there's a vertex in the bottom has like 0 neighbor in the parents set, then of course you cannot make it. So you'd better have some mean degree condition, and also you have the expansion, like the large size expands, that will do the job. Right. And ideally in the proofs, I mean the GMP you don't care about them because you can expose new random edges. But in the pseudo-random case or sparse pseudo-random case, the naive way is to choose the bottom set to be random. You may not really have it completely random, but at least let it to contain like a part of it is completely random. Namely, like half of it are random. Then the vertex on the top will have good degree to the small random set, hence to the entire bottom set. And later I will tell you that's where the that's where this random graph argument, that's where the Montgomery's argument breaks down. Otherwise, the problem is like done, like completely solved by him, by his proof. No, sorry, let me just say here. So the problem is when you do almost spanning tree embedding, you don't have any control. I mean, if you just apply the result of Alon, Krivelevich and Sudakov, or Johansson, Krivelevich and Sudakov, you don't have control on this the parent set. It's not necessarily random, and namely, you look at the vertex from the bottom, you may not have good degrees to the top. But the other side you can, because you can choose or like reserve a small set like of size epsilon n so that they have good degree, but not the other way, not necessarily the other way. So in some sense, to prove it for sparse expander, you might be like thinking, oh, I want a smarter or a better embedding of the almost spanning tree, so that part of the parent set has good is somehow random. It captures a mean degree. Okay, so what we did about the first result in the bipartite whole situation, we found that actually we could do one more step. So what Krivelevich result says, your tree either has many leaves or many long paths, bare path, right? What about we remove these leaves and then see what happens for the other tree? Namely, so if we remove all the leaves of the current tree and the resulting tree still satisfy or must satisfy Krivelevich theorem, either it has many leaves or it has many bare paths. And this like extra round or one round of deletion already results two types of trees. The first one has many pendant stars. Namely, after I delete all these leaves, I still see leaves, and this leaf will be pendant stars. Another one is, I call it pendant star because there is no other like length 2 path here because it becomes leaves. And the other case is you have this, I don't know, we call it caterpillars. Namely, when we delete these leaves, we see a bare path. Okay, like this right hand side, this green one, this is not the bare path in the tree, but after we delete the first round of leaves, they become a bare path. Right. So this gives two cases, and that's where our proof strategy goes. We split in two cases and solve them separately. So let me first explain the many caterpillar case. those are the point. I mean, the key points of in the proof. Namely, I didn't draw other parts of the trees. I just focus on these caterpillars. So, namely, you have a long bare path, and then with some leaves attached to it, but it's only like level 1. You don't have like longer legs. I mean, I don't want to call them legs later. So how do we do this? And this is a tree. This is a tree, and we want to embed. So when we do the embedding, we can first reserve random sets X and Y, and also W and L. Those are the image points of these bare path, these caterpillars, and then we can put them together, align them up, and also we can do we can build the multiple connection. So this is similar, similar to Montgomery's work. In his paper, he also need this multiple connection, but somehow we don't really need his proof, because we are much better. We have mean degree gamma n, so we have much stronger condition. So it reduces to another problem, like finding transversal cycles in multipartite graphs. But still, we can make it this multiple connection, and then it remains to attach the leaves. That part is a little bit tricky, because for the caterpillars, you don't know where the legs are, and then in your embedding, you cannot guarantee all of them, all these vertices, the images have high degree. So you need to identify which vertices, on which vertices you need to put legs. But you can still make it this way, or you need to do it this way. And then to make it work, we actually need to partition and actually positioning the starting point of the bare path. Not the bare path, but the path. So namely, we randomly partition the trunks into trunks V1, V2 until Vk, and then when we do this before we do the multiple conjunction, we already make sure all the vertices with legs will go to V1. Sorry, I'm wrong. At least a portion of them with legs are we align them so that they are in V1, and then to make sure we can embed the legs. Why? What I said probably doesn't make sense. This is because when we do this multiple connection, we have some legs, but we need to make sure we have many legs for the last step of the last step of the star matching. We cannot have them super small. If we do this multiple connection and you tell me at the last step you need to embed log n legs, this will be super hard, and we screw up because we cannot control size log n. That's why we require it has epsilon n legs, and we need to know where they are, so that at the end, actually in this picture, this legs in the legs originated from V2 until Vk will be greatly embedded. The second last step. And the last step is to find the star matching from the vertices in V1 and the leftover of the leaf vertices. Just like we go this way. We need to make sure we really get or locate those vertices with legs. Not like they are helping us, but we need to deal with them together. Right. Okay. So and now any question or I will move to my iPad. Okay, so I'll stop share for half a minute with airplane. Okay. So here we go. So we had the case many caterpillars, and this is a case of many pending stars. But again, I want to start from, so what is that about? About GMP? I said it, but essentially, you can grow an almost spanning tree, and then you finish by star matching. This is in GMP. And secondly, what's wrong with it? What's wrong? The reason is for the vertices here, they may not be random. Namely, they may not have good degree. For vertices in the bottom, may not have the good degree to the top. And what is our goal in this case? Yeah, I wrote it here. Like, I want to plant a small random set in the second last level. Namely, I don't need the entire second last level to be random. It will be good enough if I have a small set, like a positive proportion of it, to be random. And also the last step, last level, maybe this is random. The red parts are random. And then I can do the star matching. But by the lemma, I didn't read it, but I said if you have parts of random, then you can do the matching. Then you can do the star matching. Maybe I'm just waving my hand, but I want to say this will be good enough. Right. And then the third is what we actually do. What we actually do is to relax one more step. Say this is the third last level, and this will be the second last level, and this is the last level. And we first embed this part, so it's almost spanning tree. And now, but when embedding it, we could reserve a random set for the bottom. And now what I want to do is I want to embed the L prime, the second last level, and make sure the red set, I call it B. I want to make sure B is, I will be happy if I make B entirely in L prime. Okay. But I won't make it actually. What do? I will just apply the assumption. So the assumption here is alpha star G is little fan. Yeah, sorry, I'm like crossing a couple of results. Maybe I don't make it clear. But here is the case. We have mean degree. We have mean degree epsilon n and alpha star G little fan. This is the case. And then essentially, I look at a small set. I want to plant it here. I look at its parent set. I just do greedy embedding by the alpha star condition. I won't finish. I will not be able to finish. I will leave. I will stop. Like leave a set aside. But this set has sets smaller than alpha star G, which is say smaller, is a little of n. But this is good enough because we are trying to guarantee like epsilon n minimum degree. And if we select random, it will be say epsilon square n. But we are leaving out another little of n. So this epsilon square n minus little of n will still be good enough. Namely, we lose another half. But still, we capture the degree of the red set B, although we didn't really make B entirely embedded in. And then by the definition, we can protect or reserve a random set in L so that we can finish the star matching. Yeah, does it make sense or too fast? Or... Yeah. So yeah, again, my goal is to completely embed B in. Then I'll be happy. But although I cannot make it, my mean degree is really big, so I'm still happy. But next step, I'll tell you, I mean, in the sparse case, this is not good enough. So we kind of made it by looking like one more step of this peeling. Oops. What's wrong with my slides? Ah, sorry, in the front. Yeah, sorry, I somehow messed up the slides order. Right. So, I was at the wrong page. That's why I felt it was a little bit confusing. So this is the correct page, although I reproduced all the pictures. Yeah, this is the case where we have the mean degree and alpha star condition. Sorry, I was at the wrong page. And yeah, for the many stars or many pendant star case, we just consider it's enough to consider, not enough. I mean, in this talk, we only consider complete delta area tree. This will be a typical example for that, although we may really have different kinds of trees and need to look at them. Okay, so sorry, so this will be the proof of the mean degree and the alpha star condition result. And next one will be the sparse expanders. So in this case, we actually split into 3 cases. Actually, that idea of doing one round of leaf deletion inspired us for looking at this. Of course, that one will break down there. So what about we do more peelings? Namely, you take your tree, remove all the leaves, and look at the resulting tree, remove all the leaves. And you can do it many times. So we can do it k times, and that we get out. Like in our proof, we summarize into 3 cases. They are like this. First, you see many leaves. The first case is you see many leaves, like namely, even after you remove the k times, you still see many leaves. So this must be the case you have. This is where this is the case of this delta area tree. Yeah. And secondly, you may see bare path. But the bare path, after I delete leaves with k rounds, I see bare path, many bare path. But actually, this actually corresponds to 2 cases, or we have to deal with in 2 cases. Firstly, is you really have bare paths in T. You really have bare path in T. This is possible. On the other hand, your bare path may have a bunch of these trees, small trees attached to it. And though you delete, you're kind of, I'm seeing many leaves, until one step you see, oh, I see a bare path. So these 3 cases are kind of different. And then for our proof, essentially the bare path case, we kind of steal from the Montgomery's proof. Yeah, then it's done. And then the bare path and leaf, the first and third case, these 2, we kind of have one way to deal with it, which I will try to talk about in my remaining, 5 minutes. And but I will only talk about the first one. I will only talk about the first one, again, the delta area tree. The other one is just you have a bunch of small trees like somehow attached to different places. And then we can deal with it similarly. By kind of similar techniques, but somehow they are different. Yeah, because you see a path rather than many leaves. Okay, so right, that's where I tried to put not this. Yeah, this is the first case. We have we currently have this d over lambda, the spectral gap, at least delta to some power, it doesn't matter, of essentially delta to the power of a root log n, and we want to build a spanning tree. And we have like many pendant stars, but again, you forget about that. Just think about we have delta every tree or complete delta every tree. And the goal is, again, is to plant a small random set in the second last level. Then we will be able to use star matching to finish the embedding. And for here, so yeah, I will just tell our strategy. And this is the second last level. And this is the last one. I want to plant a random set here. I'm really against any loss in my random set. Before it kind of works, I was trying to pin down a set of size epsilon n, and I can lose another like epsilon square n because my degree is big. But now, if you look at the random set, even if there are sets of size epsilon n, the expectation of degree will be epsilon n times d over n if you select random set, which will be epsilon d. And this could be really small because in our situation, our d could be a subpolynomial. It's still delta to some root log n, like I'm not really dealing with constant degree expander, but still it's still like some subpolynomial. So getting this epsilon d is really small. When embedding this random set, I was calling them B, maybe, and C. I really want to embed the entire B there. Or tell me maybe I can omit epsilon d over 2, but that's really small. Maybe I just put all of them in. So this is the difference. And for that, given a partial embedding, I don't care. Maybe your partial embedding and only occupies like half of n vertices, doesn't matter. And now I have a random set down there. How can you put them in? Like I want you to embed like every vertex of B, all of them there. And apparently we don't have any good idea. Our idea is to, from a set early enough to build long path, maybe not very long, and make them connect. So these are multiple path connection. Yeah, essentially that's what we did. Right. And if you just start with a weak, very weak expander, or for example, their question or conjecture, then what do you need? The path length need to be like at least some little of log n, right? If you push the spectral gap to be a really huge constant, then you need a like small log n. And for that, we don't know how to do it. I will explain why. But in our proof, we choose length to be root log n. Okay, this is the length. I use h because it's kind of the height of our like in the tree if you look at it vertically. And this is not done because we only built those paths, but actually in the tree you could have those branches. This is stupid. Not from the root there, but from other places, you could have other branches attached to it until this level. Essentially, this where our bottleneck of the proof comes from, because when I reproduce, let me call this the size of this set M. And I'm saying I want to do multiple simultaneous connections. So on the top, this set also has size M, right? So I'm doing this M multiple connection. And for each of them, I also need to deal with the branches. The branches also have height, root log n. So the branches will have delta to the power of root log n, like vertices or the order of size this. So the blue part and the black part I'm talking about, of course, it cannot have size n. So that's where it comes from. So for that, I can repair. Sorry. So this inequality tells how big my B could be, right? And for this, my B could be n over n over like 2 to the root log n. That's a small proportion, but still nearly linear. My pseudo-random condition is good enough to control not size of this size, so that I can finish the star matching. That's what we can do. Because anyway, we are not in the optimal case. If D is really multiple, is really constant multiple of lambda, then we can only control size of epsilon n, like linear size, right? But we can control a little bit more. But that's not the problem. The problem is we can only do this reconstruction or multiple path connection with height root log n. Yeah, and this path connection, we actually use a result of Montgomery, but we can also prove it barehanded. Maybe Hong already knows how to prove it. It's just do what you can do. This like grow until they meet, but somehow you need to be a little bit precise to control the exact length. And this black part is reconstruction is also some greedy or extension. Yeah, and right, and that's it. That's the proof. And the conjectures or the open problems are just yeah, the ones I mentioned in the talk. One is for the tree embedding, spanning tree embedding. One is for the Hamiltonian cycle. Somehow they are conjectured with the same threshold, spectral gap to be constant. And this bottom one is proved recently. The second one is proved recently for D is a polynomial. And yeah, that's it. Thank you.
Any questions?